All right, good afternoon, everyone. I'm Rebekah Gilbert, and I teach math at the University of Illinois here in town in Urbana-Champaign. And today I'm going to talk about Mathematica for any size class. And the thing I want you guys to walk away from today is the idea that no matter what your classroom environment is, there's actually something from Mathematica that you can use in your class environment. And this actually comes from my experience over the last few years at the U of I, and I'm very thankful for that experience. So to begin with, well, how did I first get introduced to Mathematica? In contrast to many presenters in the education world who talk about Mathematica, I'm younger than Mathematica. So I was not even here, much less in Urbana-Champaign, when Stephen Wolfram and company were testing Mathematica out for the first time. Instead, my introduction to Mathematica came when I was at my college years, my alma mater, Grove City College in northwestern Pennsylvania. They had us do Mathematica assignments in Calc 1, 2, 3, differential equations, and theory of statistics 1 and 2, along with other extraneous courses here and there. But the idea was, I thought that was completely normal undergraduate experience. It turns out it was not. But that experience was very beneficial because in 2012, I was hired to oversee the Calculus and Mathematica, the C&M program at the University of Illinois here in Champaign, and actually to oversee a lot of the transition that was going to go on with that program. So in this position, I've been doing a lot of curriculum development, and it is through these experiences that I want to talk about the fact that you can use Mathematica whether you have a handful of students or whether you have hundreds of students. You have to make some choices into what you will keep and what you won't be able to keep, but the idea is that you can still use some aspects of Mathematica as you go and teach your courses. So for those who might not know, what is the Calculus and Mathematica program? Historically, it set the precedent for Mathematica to be incorporated as the computer algebra system of choice at the University of Illinois. It was started by 3 professors, Jerry Yule, Horacio Porta, and Bill Davis of the U of I and Ohio State, respectively, Ohio State University. Where were we? Okay, it was first piloted in the spring of 1989 at the U of I. And the ideas behind this program were based on very strong views of pedagogy, that students should be experiencing the math through the realm of Mathematica. And this class structure was drastically different from anything that you would see 25 years ago, and drastically different from many of the courses if you go into a university today. So how was it different? How did these classes look? The main difference was that students spent a majority of their class time in a computer lab working through Mathematica notebooks. There were usually no traditional lectures associated with these classes. The idea was to experience the math personally through the Mathematica files. And so they constructed an entire curriculum around this idea, and it had a sequence of Mathematica notebooks. And so each lesson had approximately, or on average, it usually had 4 parts to it. The first part was called the basics. This would be your preliminary textbook portion. The second part was the tutorials. Now that we've learned some concepts, let's actually see it in some worked examples. Let's apply it and see how we can use this practically. And then the third file was what was called the give it a try, but really instructors were told to use this to create the homework assignments. So this is where you would get the questions for students to complete for homework. And these, again, all Mathematica notebooks. The fourth file that was typically included with most of the lessons was called a literacy file. And all this were short questions that were very conceptual, minimal computation, just a quick check. Did students pick up on the concept we were trying to get across in the overall lesson and the materials that they should have progressed through at this point? So they created these notebooks, and the goal would be to have the students spend their class time working through the notebooks and then completing the homework files. And those were submitted electronically, groups of 2 to 4 students type of thing, and then personally graded and returned to the students with feedback. They did this from Calculus 1 up through Calculus 3, differential equations, linear algebra, and probability and statistics. This program ran for over 2 decades at the U of I. And it ran in many other schools around the nation, especially during the height of the calculus reform movement. And it's what led to the creation of NetMath, which is the U of I's online and distance courses. And so this is what brought the creation of NetMath in. But as I noted, I was hired to kind of oversee this program, or rather oversee transitions that the math department was going to be making with this program 2 years ago. And so what I'm going to talk about now are, in increasing orders of magnitude, the ways that you can use Mathematica depending on the number of students and the types of students that you have in your class. So here are some recent developments and recent experiences that I've had in terms of, we'll go up with, first we'll start with on the individual level with students, what you can do. When you have class sizes of 30 to 60 students, what you can do there. And then we're going to talk a little bit about what we're doing this year at the U of I when we're reaching 400 to 500 students in a semester with Mathematica. But then at the end, I kind of want to challenge the idea that there has to be a cap on the number of students you can reach. And I think that we have a lot of potential as users of Mathematica to reach more students than we are doing right now. And I'll talk about that at the end of this. So first, what happens when you have individual students? So actually, this is not quite a specific class that I was asked to teach, but I've had a few individuals over the years request to do honors projects with me. And this provides a great opportunity to really let them explore Mathematica on their own terms. So since it was a Mathematica-based class, I said, okay, well, go ahead and write some Mathematica demos and write a paper, and we'll constitute that. That will be your honors project, because that's going above and beyond the standard requirement for a class. And so last fall, I had 2 students who wanted to do things in Calc 1. And I said, well, let's look at some root finding techniques. And so they were able to, they looked at, trying to think of the techniques off the top of my head, the Newton's method, the secant method, and bisection method. They looked at and explored different root finding techniques, created demonstrations in Mathematica to visualize what was going on, to compute these root finding techniques, and to really understand at the basics what was going on. What are the kind of the conclusions that you can take from doing one-on-one projects with students? Overall, these projects were pretty positive. I would say that the students did a really excellent job with these, and the reason being, when you look at things and you take a step back at the end of the semester, is students took the initiative to do these honors projects. And then beyond that, they got to pick which root finding techniques they would talk about, and so they were able to pick and choose the ones that they found interesting. And when you have that happening, you have students showing a greater interest in something they're choosing to construct than if it's just a typical required assignment. So if you happen to be able to have the opportunity to do honors projects with students, having them create Mathematica demonstrations and working through and having them learn how to do that is actually a really good way to incorporate Mathematica one-on-one. But obviously not all of our classes are one-on-one. We're not all tutoring when we're teaching. And so over the years, I've had the opportunity to teach 30 to 60 size student classes. And these sizes are actually most comparable to the old calculus and Mathematica course sizes. And so this one is, on the sum level, the most comparable to what had happened in the calculus and Mathematica program. So I did this with Calc 1, 2, and differential equations. And depending on the class course number and course credit, I would meet with the students 1 to 2 days in a traditional lecture format, and then 1 to 2 days in the computer lab. And in contrast to other institutions that have attempted to incorporate, Mathematica or any of the competitors, a key factor was, as the instructor, I also ran the labs. So there was a very fluid transition that you would not be seeing if you read about the papers of other people who are trying to incorporate technology in their classes right now. So what did I do? Primarily, I did what I had been asked to do, and that was basically to capitalize on the improvements to both Mathematica in the last 25 years and in our users, the students' familiarity with computers in the last 25 years. We can all probably admit that there are students who are much more comfortable with technology out there than we are as the instructors. And so at the request of the department, I wrote new assignments that both took advantage of Mathematica's improvements and students' improvements when it comes to being able to use technology. And so these new assignments taught students how to use Mathematica commands for themselves. That was really the primary goal of these new assignments. And as we see, it was fairly successful in some classes. And how did we do that? How did we teach students to basically take command of Mathematica for their own self? First, we gradually introduce students to the commands in the assignments. And the commands introduced in an assignment were directly relevant to the concepts for that lesson. So we aren't going to introduce the integrate command when we're talking about derivatives. And we introduced the limit command at the beginning of the semester when it was relevant. So they were directly relevant to the concepts of that lesson, but we didn't just throw it to them. We built from the basics, and we first said, here's the anatomy of the command, and here's a quick example. So if you want to compute a limit, here's what it will look like in a generic sense, and here's an example. And so we taught them through short practical examples, but in the homework assignments that the students had to work through, they weren't just short practical problems. They were often long and involved thought processes that had to be going into some of the problems. And so we said, when you don't know how to do something with your command, refer to the documentation center. So we empowered them by turning to the greatest resource out there, is to actually learn for themselves how to continue to expand their understanding of the commands in Mathematica and all of their options. Another feature that I included with these new homeworks were that I wrote problem kind of descriptions. So I told the students what commands they could expect to use. Now, some of them were very creative and would include commands that I didn't teach them, but they went into the documentation center and found on their own. We also included what the students should learn from answering the question and why we actually had that problem in the overall homework for pretty much every single homework question. And very similar to how the Calculus and Mathematica courses had been run, we had homeworks submitted by groups of 2 to 4 students, and then they were personally graded and returned with feedback to the students. But the primary change here was that we really capitalized on the advances of the last 25 years and really updated the material and made it a little bit more modular, which we'll get into later on as the primary benefit. So just some brief examples of how we did this. I went down and I just tried to type from memory a sampling of the commands that students learned. This is in Calc 1 over the course of last fall and last spring. So those are some of the commands that the students learned. And there are certainly ones that you might expect to see, so the plot command and some of the options. And then one, the prime pi, that came up in a random problem, but it was still one that the students got to use, so it was kind of fun. I figured I'd just put up here 2 or 3 visualizations from Calc 2, so a course that I taught last spring. Here we're looking at visualizing and computing terms of a convergent sequence. So often we talk about the word convergence and divergence, and in very abstract senses, students don't get it. But in a very concrete picture, students can look at that and understand that sequence is converging, in this case, to the value of 2. And at least gut reaction understand what we mean when we're throwing around these mathematical terms. This is a personal favorite that students liked. It is a visualization of the alternating series test, or rather just looking at an alternating series. So in blue, you have the terms of the series, and then the orange color, blue and orange colors of the U of I, the orange represents the partial sums. So students can see that the changes in the partial sums corresponded to the actual terms of the series, and they could gather this information about why the alternating series test in this case worked and what it really meant for these series to be converging. And of course, Calc 2 is not complete without a visualization of our favorite, Gabriels Horn. The object that has infinite volume but finite surface area. Students are always amazed when they say, you mean I can fill it, or sorry, finite volume but infinite surface area. You can fill it with paint, but you cannot paint the surface area of this object. Now, what are some conclusions from updating and creating new homework assignments that students did in groups? The first conclusion is that students actually had far greater of a personal investment when I used these new homework assignments than to the previous course materials that I had at the U of I, because they realized that they were able to solve problems on their own in Mathematica. We taught them how to use the commands, and by the end of the semester, I can tell you that absolutely every single student could use the plot command without even thinking about it, and probably many more. But the idea is when they realized that they were able to personally solve their problems, they have a lot more of a personal investment rather than just taking, a page of code they were able to put a personal interest into solving their homework questions. The second conclusion is an interesting one, but I think it's similar to a lot of the other studies that are being done right now. These homeworks actually help to differentiate, for me, the diligent, eager-to-learn students from those who were less motivated. So I'm comparing Calculus 1. I taught it last fall, and then I taught it again in the spring. When I taught it in the fall, the average course grade was 84%. The students in the fall were very diligent. They were hardworking. When they encountered gaps in their previous learning, they put in the effort to improve on their mistakes and to fill in those gaps from anything they might have missed in high school. The students in the spring, however, let's point out some differences. I was able to revise a lot of the material from the fall that fed into the spring material, so they should have had, better material. I was also meeting with them one more day a week than I had been in the fall, but at the end of the day, their course average was a 69%. These students, on average, came in a lot weaker, and many of them did not put forth that personal effort necessary to improve over the semester. All of the students in the spring had seen Calculus 1 before. All of them had failed Calculus 1 before. Some of them would just skip midterms. They didn't really care too much to put forth that effort to do well. So what was the impact on their end of the semester assessments? From the fall, the students who worked hard, 50% of the students on their course evaluations said that Mathematica, when they were asked what was the most beneficial aspect of the course, 50% listed Mathematica in these assignments that we did. And some of the quotes you can see right there. Mathematica allowed me to visualize many parts of math I didn't understand before. So for these hardworking students, 50% of them listed Mathematica as the most beneficial aspect. Compare this to the spring. 21.4% said that Mathematica was beneficial, but 28.6% of the students said that Mathematica was the one aspect of the course that they would change. So this goes to show that for the students who really are motivated and want to learn, Mathematica, especially the visualization and being able to see things and have that quick computation, it was valued and appreciated, and it helped them. For the students, however, who didn't want to personally push themselves, it was not viewed as favorably, and it did not help them as much. So this was useful, it was beneficial, but if you're a student at the University of Illinois, an average student, you don't get to go through a class of 30 to 60 students. The average student at the University of Illinois, when they take calculus, will go through large lecture sections of calculus that are going to be 200 to 250 students per lecture section. So the question that the department wanted to ask this year is, can we still use Mathematica in the large lectures? And that question I answered with yes. To some extent, we can still use some aspects of Mathematica with the large lecture classes. So what are we doing this year at the U of I? This fall, we're working with 2 large lecture sections of Calc 1. And then in the spring, this upcoming spring, we'll be following up with 2 large lecture sections of Calculus 2. And these large lecture sections, I said 200, 250 students. They'll meet 2 days a week with a faculty member in the classroom. And then they'll break down into small TA-led discussion sections, 40 to 50 students, the other 2 days of the week. And each section, when they meet with the graduate TA, in keeping with the tradition of having the peer advisors, we kept 2 undergraduate assistants to go into each of those discussion sections and help the graduate student out. But in doing something on such a massive scale, we had to think and answer a lot of questions and say, what aspects of Mathematica can you scale up if you're going to be doing a course of this size? And the conclusion we came to is that you could not personally grade group homeworks anymore. It is not feasible to do it on this scale, but we didn't want to lose what we saw from the smaller classes, that visual benefit and the computational benefit. We wanted to keep that. And so that's what we said, well, let's go ahead and develop a bunch of CDF demonstrations. And the way we're going to incorporate it is sometimes in the classroom. I definitely bring it into the classroom. But when they're doing their active discussion worksheets with the graduate TAs 2 days a week in their small groups, we're going to have some of those questions be ones that require them to access a CDF. And so what we've done is normally the students would go to their TA section and they would work in groups of 2 to 4 on paper worksheets. And the University of Illinois is very excited to be doing a lot of active discussion learning in these sections. And so we're keeping that energy in these discussion sections, but now the paper worksheets, about half of the questions this semester are directing students to CDF demos that I've created. And some of them, it's helpful to visualize things, and other times they need it for computation. So one thing to note, though, is that in using these CDFs, students are not going to be using Mathematica commands or code anymore. That is one thing we had to let go of. But the good news is that these CDFs are providing students with that prompt computation and concept visualization, which is certainly an improvement over static textbook figures. We can all agree that the manipulate command is certainly something that we can't live without now. At least I cannot live without in the classroom. So here are 2 examples. I'm going to show you a bad example and a good example of how you can use a CDF in class. So first, the bad example. When you're dealing with related rates, you sometimes get the angle of repose question of if you're pouring corn out onto the floor of a barn, what's the shape that it makes? And so we had this manipulate that kind of shows the corn pile growing. It's a good graphic, but really it didn't do anything for students. None of the students said they liked it. In fact, some of them said they would have just rather had, a 2-dimensional sketch on their paper. So there really isn't any point to including this as a demonstration. What I'm about to show you, though, is something that students only halfway through the semester have already said is one of the best things they've seen in this course, and that is a visualization of the mean value theorem. So I'm going to shrink the size just a little bit so that we can see this the entire thing. But the mean value theorem, when you first present it in the classroom, students' eyes glaze over. And that is because it's a bunch of math jargon, and if they don't stop and think about it, they're really not going to understand what you're talking about. It's just a bunch of symbols on the paper. So what we wanted to do was have a graphical representation of the mean value theorem. And we told students before they went to do that worksheet that we want you to use the graphical to make sense of the mathematical. And other times, we'll give them a graph and say, use the math to explain what you see in the graph. So the mean value theorem says that for any 2 points that you pick on a continuous function, there's some point between them that has the same instantaneous rate of change, or the slope of its tangent line is equal to the slope of the secant line between the other 2 points. And so students were able to play around, pick any 2 points, A and B they wanted, or even have manipulate basically do an animation of what's going on. And students would sit there for a few minutes, but they all came back the day after they did that worksheet in one of the sections, and they said, this helped. They now understand what the mean value theorem is talking about. Because they had this concrete visualization, they were able to use the graphical to make sense of the mathematical. And so this is what I would say is a useful implementation of the CDF in the classroom or in the discussion sections. The students got to experience what it really means for the mean value theorem visually to make sense of what we say when we're at the board. So even though we're only halfway through the semester, I do have a few conclusions based on the data we've been collecting. And the first conclusion, not even based on data, all of these CDFs may be modularly incorporated into any course. I substitute taught for someone yesterday who incorporates absolutely no technology into his Calc 1 section, and I still took a CDF in there of Riemann sums. And that's because students don't really need to have any previous experience. They just need to be someone who's comfortable using a computer screen. And pretty much all of our students are at this point. We did have to trade students learning how to personally use Mathematica on this scale, but in exchange, we're still having students harness the power of Mathematica without that steep learning curve. We're still getting all the benefits. And in fact, we're extending the benefits to an order of magnitude more students than had previously been reached. The last conclusion, though, is one that every teacher faces. While these concepts are beautifully demonstrated in CDFs, the CDFs themselves are unable to force students to apply themselves. And this is, again, a similar concept to what we saw in the conclusion from those 30 to 60 student classes. You cannot force students to apply themselves. And this can be detrimental for students on exams, no matter what size the class is. But we are collecting a lot of data on how this is going this semester. So probably in another year, we'll have more concrete numbers to give for it. But one thing I wanted to conclude with is I don't think that 400 or 500 is really an upper bound. I know it's a rather large class. We're going to have a large sample size to work with. But I don't think there's actually an upper bound to how many students you can reach. Online classes are here to stay. There's not much question about that. The question is, how do we utilize them? What are we going to incorporate with them? Many studies have been done that show online courses work best for self-motivated students. These are the same students who appreciated Mathematica in the smaller scale classes. So in some sense, online classes working best for motivated students, it would be great to be tying more Mathematica into that. But like Harvard, I want us to question whether we need to restrain ourselves to the word classroom or course. Harvard now considers online learning activities and the idea of modular built things. By popular choice, when students need a reference, they turn to Paul's online notes, or if they want a video, they turn to the Khan Academy. But right now, they are not turning routinely to the Wolfram demonstration project, which is really the strength behind what a lot of educators could be using. And so I almost think that the way Mathematica could be incorporated is not so much thinking about a course, but thinking about creating the 21st century version of Paul's online notes, or creating the 21st century version of all of these modular explanations of calculus or differential equation topics that have the CDF demonstrations, or anything else that Mathematica is coming out with that is completely beyond my understanding right now in the cloud. But the idea is there aren't conclusions to this yet. We're the ones who will be writing the conclusions. And there's a lot on the demonstrations project, but we need to make it what becomes the next standard when students need to turn to a concept and understand it better. So there is not an upper bound to how many students we can reach. The question is whether we will put our resources towards becoming the next leader in math education. Thank you.